So we're going to look at reversible versus irreversible processes. This will be very important for later on when we start discussing the idea of entropy. Now, this chapter is titled The Second Law of Thermodynamics. And the second law of thermodynamics states that for a closed system, that the change in entropy is either equal to or greater than zero. And when we're talking about reversible versus irreversible, we're really talking about, does the entropy change? Okay. Second law says that basically the entropy for a closed system can only increase. Generally, if it's reversible, there is no change in entropy. If it is an irreversible process, we have a sudden increase in the entropy, and we can't restore it to its original state. So again, let's define here. A reversible process is one in which every state along some path is at equilibrium, and one for which a system can be returned to its initial state along that same path. So as long as we proceed in any of these thermodynamic processes slow enough such that we're never out of balance, we're never out of equilibrium, okay, we can return to that original state. If, however, we lose thermodynamic equilibrium, maybe we have turbulence build up in the system, maybe we heat part of the system unequally, okay? Generally, even though we can get close to the initial state, we can't completely return it to its initial state, and the process is at least somewhat irreversible, okay? So reversible processes, complete idealization, okay? They don't actually happen in nature. There's always some friction, there's always some turbulence, there's always something that is going to make it difficult to return exactly to the original state. Let's take a look at an isothermal process and see how, if we go slow enough, we can get pretty close to the original state. Now, again, let's say that we start at a initial point, let's say down here. We're going to make to a final point right here, and then go back to the initial state, okay? As long as we proceed slow enough along this path right here, okay, we should, in theory, be able to compress the gas, get it to this final state, and then go back down and return to its original state, okay? So we can compress the gas, expand the gas along the same path, and the gas would obviously have to be in contact with some thermal reservoir in order to keep the temperature constant. So what would that look like? Well, we can imagine having this piston, okay, the cylinder, in contact with some type of thermal bath, and this thermal bath is large enough where it can absorb, as much heat as you can dump into it, and it can give off as much heat as you can get from it. So again, we can imagine using this mass right here and slowly allowing that mass to compress the gas, okay? And basically, if we do this slow enough, this would, as it compresses the gas, allow the work to leave the gas in the system as heat. Remember, if we don't allow the heat to leave, it's adiabatic and it's going to increase in temperature. And then we reach this state right here, and then we could, they don't show removing the mass right here, but if we remove the force on this, the gas would expand again. And if it's in contact with this thermal bath, as it expands, it would be able to absorb heat from that bath and stay at the same temperature, okay? So again, the external pressure is slowly used to compress the gas. It wants to heat up, but any heat is allowed to leave through the bath. And then reversing the process, the gas is allowed to expand, but heat flows back into the system. So again, this would be a reversible process, but any turbulence within the gas, any uneven heating would make it hard to get to exactly the original state without some additional outside help, okay? In fact, if you think about the system, we place a mass on here, it compresses the gas. To get the gas to uncompress, we'd actually have to remove this mass, so that would sort of be our outside help there. Now, for an adiabatic process, instead of having a thermal bath that we can dump heat into or take heat away from, we can imagine an isolated system where no heat enters or leaves the gas. Thus, it's going to be adiabatic. So again, we're going to use external pressure to slowly compress the gas. PV equals nRT. We do work on the gas. This raises the internal energy of the system. As work is done on the gas, the temperature goes up, temperature rises. And finally, after we're done here, again, we're starting at this initial point right here. We compress the gas, it gets warmer and warmer and warmer. We reach this point right here. If we go up and then back down slow enough, we should be able to reach this initial point again. Okay? So again, this is completely theoretical. You can't completely retrace the path because to some extent, these thermodynamic processes have some increase in entropy, okay? Again, perhaps due by friction, perhaps due by some type of turbulence or uneven heating. But again, we can sort of approximate this. And this is going to be important to try to analyze the efficiency of different systems and design the most efficient system. So again, it's going to be very much connected to a word I keep using, entropy. And entropy is really sort of a measure of how much energy is no longer available to do work. Again, we'll get to that a little bit later. It's a very abstract concept. Now, again, the second law of thermodynamics is very much connected to a later topic we'll talk about, known as entropy. But there's a Clausius statement connected to the second law, and it says, it is impossible for any system to operate in such a way the result would be the transfer of heat from a cold reservoir to a hot reservoir without the use of external work, okay? Now, you can conserve energy and you can actually move heat from the cold reservoir to the hot reservoir, okay, and not violate that conservation of energy. If I take 100 joules from here and move it to up here, that's not a violation of conservation of energy. All the energy is accounted for. So the second law of thermodynamics is something that's different, okay? It basically says, well, up here, the molecules are moving faster than down here, okay? So if any of the molecules up here at the higher temperature interact with any of the molecules here at the colder temperature, the hotter molecules are going to tend to give off their energy more to the colder molecules rather than the colder molecules giving up their energy to the hotter molecules, okay? They're going to thermalize, they're going to equalize out. So generally, heat would naturally flow from the hot reservoir to the cold reservoir, okay? And when we have more energy up in the hot reservoir, I should say a higher temperature in the hot reservoir than the cold reservoir, we say that this is a more ordered system. We've separated the hot molecules from the colder molecules, and thus it has a lower state of entropy. Now, as I allow the hotter molecules to give up their energy to the colder molecules, allow the heat to go down here, we would expect the temperature in the hot reservoir to go down, while the temperature in the cold reservoir would tend to go up, okay? And again, this would be associated with less energy available to do work, okay? An increase in the amount of entropy. So, conservation of energy is not the only law that is going to dictate what happens. We also have this concept where there's only so much available energy to do work, okay? Even though in a system such as this, the hot reservoir and cold reservoir, if they're isolated, we don't really change the amount of energy in the system, okay? So that's very, very important, and very important to the efficiency of engines. So again, if you want to identify an irreversible process, an example of an irreversible process would be heat flowing from the hot reservoir to the cold reservoir. Okay? And when this happens, we can't spontaneously just say, okay, we've taken the energy from the hot reservoir, now we're just going to put it back to where it was. Okay?